So we welcome Annette Maier from Aachen. She'll speak on parameterized differential equations in patch.
Yeah, I would like to thank Alexei very much for inviting me to give a talk here. I'm talking about Galois theory of parameterized differential equations and the inverse problem in that context. And I'm working over the following kind of fields. So the field F is a rational function field over a field of formal Laurent series over any field K of characteristic 0. And any differential equation in my talk is going to be an ordinary linear differential equation with respect to x. So the constants are just k of t. And this is an example, a classic example of an order 1 parameterized differential equation. So you can solve this with x up to t. So we can write our solution as a power series in t with coefficients and powers of log x, which is a power series in x minus 1. So that's a field where we can find a solution. And it's important for the Galois theory that this field doesn't have new constants. Okay. And so now the classic differential Galois group would be that you adjoin a complete set of solutions, so in this case just y, and then you consider f automorphisms of that field that respect the differential structure. And such an automorphism maps a solution to a solution, so it maps y to constant times y. And you can check that any constant gives rise to such an automorphism, and any automorphism is given uniquely by this constant c, so you can identify this automorphism gamma with c, and so the Galois group is GL1. However, this was not 100% precise because the constants are not algebraically closed. So instead of saying that this is the Galois group, we should rather say that this is the k of t rational points of the differential Galois group. Right? And then by tensoring upwards the algebraic closure and computing some automorphisms there, you can show that also over the algebraic closure this equation holds. So in fact the differential Galois group is GL1. And this differential Galois group is a measure of how many algebraic relations there are among the solutions. And we had an order 1 equation and we got all of GL1, and that means that y is transcendental in this case. There's no algebraic relation. So let's move to the parameterized theory with the same example. So we can also differentiate with respect to t on both of our base field f and also on that field E where we found our solution. So let's differentiate the solution twice. And then we find that there's an algebraic relation among y and its higher t derivatives. Its first and second t derivatives. So these are algebraically dependent, or in other words, y is not differentially transcendental over the base field. And now this parameterized Galois theory is built in a way that it can see such kind of relations as well. So the parameterized Galois theory is a measure of how many differential algebraic relations there are among the solutions. And so we can refine the definition. So now we adjoin also a complete set of solutions and also all of their t derivatives and higher t derivatives, and we only consider those automorphisms that commute with both derivations. So this way, such a relation is preserved by such an automorphism, and we can compute it in this example. So again, the solution y is mapped to constant times y, and then you can apply gamma to this equation on both sides, and then we get the following condition on c. So that's new, and again, this gamma is given uniquely by this constant c, so we can identify it with a subgroup of GL1, but this time we get a strict subgroup of GL1, which tells us that there is a differential algebraic relation among the solutions. And again, to be more precise, maybe just for the experts, this group that we computed was not the parameterized Galois group, but it's the rational points over our constants. And it doesn't necessarily contain all information on the parameterized Galois group is because this field is not differentially closed, but you can compute that also over any differential algebra S. You have this equation, so in fact, the parameterized Galois group is the subgroup of GL1 that is given by this equation. So that was the definition of the parameterized Galois group in this example of order 1. In general, we start with a linear differential equation of order n over this field, and then we can find a complete set of solutions in some extension field without a constant. We join all of these solutions and all of the t derivatives, and we compute automorphisms in a certain way, and then we can define the parameterized Galois group. And there's a natural embedding to GLN, given by a choice of solutions, just as what we did in the case of GL1. And inside GLN, this group is given by differential algebraic equations. So it's what's called a linear differential algebraic group over the constant. And I'm interested in the inverse problem, so which of these groups actually are Galois groups of some equations over this field F? Okay, so let me tell you what's known about the inverse problem over fields U of x, a rational function field over U, where U is a universal differential field. So in particular, it's differentially closed. We can think of it in our context as a universal closure of our field of constants KFT. And then there's this theorem, recent theorem, by Dreyfus, Michi, and Singer, which says that over this field U of x group is parameterized Galois group if and only if it is differentially finitely generated. And that means that there are finitely many group elements, such that this group G is the smallest linear differential algebraic group containing these elements. Or in other words, it's the Collision closure of the group generated by these elements. Okay, this was proved in 2011, 2012. So this is actually quite a constraint on the group. It's finitely generated because, for example, GL1 or the additive group GA, those groups are not differentially finitely generated. So the question is, which groups are differentially finitely generated? And there are some answers. For example, if the group is, this is a special case of a differential algebraic group just given by polynomial equations. And there's this characterization by Singer, which says that such a group is differentially finitely generated, if and only if its identity component has no quotient isomorphic to the multiplicative group GL1 or the additive group GA. And in particular, if you have a semi-simple linear algebraic group, it's finitely generated. And I'm interested in, over my field F, whether every differentially finitely generated group is a parameterized Galois group there. And so to have a positive answer for at least some class of groups, I actually started with semi-simple linear algebraic groups.
More is known about the inverse problem. There are more cases.
Yes, I know.
Not just this. Oh yeah, good.
Yeah, there are also some other classes of groups where you can characterize which groups are differentially generated. Okay. And so back to the field F, where I'm interested in that the field of constants KFT is not differentially closed and it's also not algebraically closed. But it's a rational function field over this field KFT, which is a complete discretely valued field. And over such a field, there's this method called algebraic patching that was developed some years ago by David Harvard and Julia Hartmann. And so, because this field F, it's a function field of the curve P1, and then there are these certain overfields, not just any fields, but very specific ones that come from geometry, but you can choose the number m. And for example, if you want m equal to 2, you can choose your fields like this. So this is our base field over QT. This is the fraction field of power series in two variables x and t, And this is contained in the field where you first take no more series in X and N and T. And similar for these are certain completions or fraction fields of certain completions of regular local rings on the curve at some points. And this F naught is, can also be written down explicitly. It's also some power series with certain coefficients. Anyways, it's not really important right now for this talk how these fields look like explicitly. But what is important is that we can write them down explicitly and we can compute inside these fields. It's just power series. And all of these fields are differential fields with respect to X and T. And there are no new constants with respect to X in any of these fields. Okay, so let's go back to the general picture. And this algebraic patching method is a theorem about factorizing matrices. So if we have a matrix with entries invertible with entries in here, then we can write it as product of a matrix with entries in here and one with entries in here. And you can even do this simultaneously, meaning that if you're given m matrices up here, you can write each of them as a product, here and so on. But the one matrix that's coming with entries in F naught is the same for each product. That's the matrix Y in this equation. Yeah. And you can apply this factorization result to differential Galois theory as follows. So let's say we have a differential equation of order n over this field F1, such that we can find a complete set of solution up here. And we call it, it's a parameterized Galois group G1. And we have, let's say we have, similarly, we have the same over F2 and Fm and so on. And these m differential equations are all of the same size n. And then the statement is that then there exists one differential equation over our field F, such that we can find a complete set of solutions inside F naught. And the parameterized Galois group of this constructed differential equation is then differentially generated by the groups, the smaller groups up there that you started with. And so this patching allows to break down the problem into smaller pieces, right? And this is proven using this matrix factorization applied to this fundamental solution matrices Y1 to Yn. You can factorize them and you can use the one matrix you get over F naught as a fundamental solution matrix for the equation you want to describe. And so now if we are given a group G and we would like to construct a differential equation over F with that Galois group, which might be hard, then this method allows us to break it down into smaller pieces, meaning that if we can find the collection of subgroups G1 to Gm of this group that generates the group, and if these subgroups are nice in a way that we can easily realize them over these fields F1, F2, and Fm, then that's enough. Okay? So instead of trying to find differential equations for big groups, it's enough to find differential equations over these kind of local fields for these smaller groups generating edge. Okay, so that's what I did. So let's assume we have a group G that it's generated by finitely many groups G1 to Gm, such that each of these groups is either a finite group or a subgroup, a strict subgroup of the additive group that has to be generated by one element, and this one element is either rational over all constants or maybe over finite extension. And it's enough if it's isomorphic to this group over finite extension. But okay, and it could also be isomorphic to the constant subgroup of Gm. So these are the elements of G1 that are constant, right? It's a linear differential algebraic group. Okay, and some other groups, some other strict subgroups of Gm, but not very many. And then this group is a parameterized Galois group of a differential equation. Okay. Okay, so as I said before, I was at the beginning interested in the semi-simple linear algebra groups. So if you have a semi-simple linear algebra group defined over our constants, then this group will split after finite extension L. And if this group splits, you can show that it's generated by groups of type 2 if it's connected. And because what you do as an algebraic group, it's generated by 2 subgroups, which are additive groups. However, these additive groups are too big. You can't realize the additive groups itself, but you can find small subgroups of these root subgroups of type 2 that generate a group. Also, this is a class of group. Group G is such that G modulo its unipotent radical is constant. For example, a unipotent differential algebraic group. And it has to be generated by finitely many elements that are rational over our constants. And such a group can also be generated by groups of type 1, 2, and 3. And this is actually a class of group if the constants are universal. Then this type of group was, this class of group was considered in a recent paper by Menchenko, Ovchinnikov, and Singer, where they have an algorithm to test whether the Galois group is of this type, and if so, they can compute it. So that's why I was interested in these kind of groups. And okay, also groups that are generated by finite many unipotent elements and constants of differential algebraic groups. Okay, so I have a little time, so I can say something about this finite extension that you may need to have, for example, for the semi-simple linear algebra groups. So let's assume you're interested in realizing the group over this field down here, but the group you have only splits over this field up here. So you need a degree 2 extension. And then what you do is that you arrange your diagram in a way that the finite Galois group acts on it, and you have to arrange your building blocks in an equivariant way somehow. And then you can show that using Galois descent for differential modules, that this equation that you constructed actually descends to this smaller field. Okay, so now back to this question that I was interested in, whether every differentially finitely generated group is a parameterized Galois group over this field F. Here's a small example. So this group G, subgroup of GL1, it's actually the Cauchy closure of the subgroup of GL1 generated by T, right? Because all powers of T satisfy these equations. And so this is a very small group generated by one element that's even rational over my constants, and I don't know whether it's a parameterized Galois group. It's easy to see that it's a parameterized Galois group once you adjoin the log of T, but I would be interested to know whether it's actually a parameterized Galois group over F, or maybe not. So, thanks for your attention.
Can you go back to your very first slide?
Oh, sorry.
I can page all the way back there.
Press Control at home.
Yeah, this one.
Okay. That's what we just.
Yeah.
Good.
Oh, you just wanted to see it, okay. Sorry.
More questions?
Can you go to the previous to last? Is that
Sorry.
I just want to see the
The last, okay, yeah.
that one, yes. Just want to read the question again, please.
Oh,
I asked the question because I mean I'm quite an amateur at this. So why do people study inverse problems in this particular context? No, I mean I don't know. I mean, like, so why? So knowing that a group is a differential group in, what does that buy you at the end?
It doesn't have a direct application.
Oh, in fact, I can comment more on that.
Okay.
It actually has algorithmic applications.
Okay.
So suppose you want to compute the group.
Okay.
And you compute the group to find some information about the solutions.
Okay.
So, and it's often the case that you have a list of groups that can possibly occur, and by doing some computation of the equations, you just erase elements from the list.
Okay.
And the smaller your list is, the easier your procedure goes.
Okay. That makes
And
sense.
such characterizations help actually produce algorithms that terminate.
Yeah.
So the criterion that was shown at the beginning over those universal fields, there exists a finite set that generates the group, is not yet very practical for algorithms. So in the papers we transform it, and for the unipotent group was discussed. So we apply it in the situations we can to make algorithmic, to find more restricted cases. So that's just a very theoretical
Yeah, but
result.
that's a reasonable application.
So you showed some classes from groups, right? So that you have discovered. Can we go back to that slide? Not just for the sake of looking at it. I have a question. So maybe it's obvious from this. So which of the cases? I guess. So suppose your group is given by equations, defining equations. Can you check algorithmically whether it fits into one of these cases? If it's one of the type.
I don't know.
Well, the first sentence.
So for some of them, what is unclear, maybe. And by the way, so the G is generated by finite Riemannian. G generated in what sense?
You proceed over universal closure.
Yeah, but generated as the smallest.
Differential finite general.
So this Gaussian closure
Yes.
of the. And so that is not clear how to check, right?
No.
So that property is.
No, I mean, even for algebraic groups, it would be linear algebraic groups. It would be quite hard to see what kind of subgroups you need to generate if it's general.
But it's still not even known whether the question is decided, correct?
Yes.
Moving to the question.
I don't know. So if you're given a group and you know that it is a differential algebraic, a differential Galois group, could you compute some example of equations?
Oh, can I compute the direct problem, not the inverse problem?
No. Given a group, and you know that it's one of your type.
Can I compute the equation?
Yes.
If it's one of my types, yes. I mean, the method is explicit because what is used is this matrix factorization.
Okay.
And then you can, over power series, you can do that explicitly. Yeah.
By explicitly you mean there is an algorithm or...
I don't have an algorithm, but you can compute it, the coefficient of the power series and
So for example, if you have if the group decomposes the way you want it, right? And each of these factors you can, let's say you can compute the equation. And how do you piece them together to get an equation for your big group?
Yes,
You can.
I can do that, yeah.
Okay.
With the matrices, yeah. But it's not that easy.
More questions? We have a few more minutes. Questions, comments? Well, thank you very much.